Good morning. Let me take one more chapter known as asymptotes. Asymptotes. Now, what's an asymptote? See, let me draw a curve. This is a curve. And let me draw this line. This is a curve, and let P be any point on this curve. You see this perpendicular distance from the point on the line. This is this much. If this point moves along this curve, say this is the point, this perpendicular distance tends to it is less now here. If P is residing on this or residing on this or moving on this curve, this is the perpendicular distance less, it becomes less and less. This is again less, and we assume that somewhere at infinity this will meet this point and this line will meet. This line is then known as asymptote to the curve. In short, an asymptote to an infinite branch of a curve, this goes to infinity, is is tangent to the curve at infinity. So asymptote is nothing but it is tangent to the curve at infinity. Let me take one more example. See, let me suppose that this is the curve. You have two branches of the curve, one going this way and another going this way. You can see that this will meet somewhere at x-axis somewhere here and y-axis somewhere here. Then we say this is an asymptote parallel to x-axis. This is an asymptote parallel to y-axis. Although this is the x-axis itself, this is y-axis itself. Similarly here, this will meet somewhere at infinity. This line, this is an x-axis, this is an asymptote parallel to x-axis. This is an asymptote parallel to y-axis. It will meet somewhere here. Okay, let me have one more example. Let this be the line, this be the curve, and this be the line. You see perpendicular distance, it is lesser, and somewhere here it will meet this line. So this straight line is known as tangent to the curve at infinity. Okay, so let me define what is the definition. The definition is that an asymptote to an infinite branch of a curve. Infinite branch. Why infinite branch? Because we say that it is tangent to the curve at infinity. So branch must, or the point must go towards the infinity along the branch. So an asymptote to an infinite branch of a curve is a straight line. Not lying at infinity. We are presuming it, such that the distance from it of any point on the curve or on the infinite branch of a curve tends to 0 as the point tends to infinity along the branch. Okay, this is the curve, and this is the line. You see, this is the point, this is the distance, this tends to 0. As the point P tends to infinity along the branch, this is the line, this is known as asymptote to the infinite branch of a curve. Now there may be asymptotes which may not be parallel. For example, if you have this figure and you have curve like this, you see there will be some line here, some line over here. This line is neither parallel to x-axis and this line is not parallel to y-axis. These asymptotes, these are to be asymptotes. This will meet somewhere at infinity. Their perpendicular relation will tend to 0. So this will be an asymptote. This is known as oblique asymptotes. So there are two types of asymptotes: parallel asymptotes, parallel to x-axis, parallel to y-axis. Parallel to y-axis, there will be some things like this, parallel to x-axis, and there are also oblique asymptotes, neither parallel to x-axis nor parallel to y-axis. This will have two asymptotes, neither parallel to x-axis nor parallel to y-axis. You see, how many asymptotes will a circle have? It will have none, because you don't have an infinite branch of a curve, so no asymptotes. So some curves may have asymptote or some may not, depends on the curve. Now what's an algebraic curve? This is 17. Now algebraic curve. This is, see, you have, say, x plus y equals, say, 5. This is an algebraic curve, a linear curve. You have x square plus y square plus xy. This is an algebraic curve of degree 2. This was algebraic curve of degree 1. While adding, this is a algebraic equation, algebraic curve of degree 2 of x cube, y cube, x square y, xy square, and nothing cubic having degree 3. This is an algebraic curve of degree 3. Separately, these are algebraic curve. This is an algebraic curve of degree 3. This is an algebraic curve of degree 2. This is an algebraic curve of degree 1. And if we add them, this is generally an algebraic curve of degree 3. If we will add 4 also, x4, y4, x square, y square, then there will be x cube y and xy cube. So finally, this is an algebraic curve of degree 3 and degree 4, and so on. There will be an algebraic curve of degree n, x raised power n, x raised power n, y raised power n, x raised power n minus 1, y raised power n minus 1x, so on. This and plus some constant, say k equals 0. This is an equation of an algebraic curve of degree n. This can be written as, if we take x from here, this will be 1 plus y by x. Take x square from, this is homogeneous. X square from here, this is 1 plus y square by x square, y by x. Take x cube from here, 1 plus y cube by x cube. Now you have taken x square, so y by x, then y square by x square, plus so on. Then last, x raised power n, this will be some y raised power n, x raised power n, 1 plus, plus so on. So this is known as x function plus constant equals 0. Function of y by x. This is x square function of y by x. Then this will be x cube function of y by x. Then function of phi n function of x, x is power n over here, plus k, this will be function of 0, y by x equals 0. This is a homogeneous equation of order 0, of degree 0 rather, homogeneous equation of degree n. There will be homogeneous degree of homogeneous equation of degree n minus 1, and this is of degree 3, degree 2, degree 1, and so on. So for now, what is the rule? I will be sending you a few pages. Before going through the asymptotes, please read down those pages. Those are basics where you can find how to find the parallel asymptotes and oblique asymptotes. I will just read out those. Rule is that if in an nth degree you have algebraic curve of degree n, if in that x raised power n and y raised power n are present, then there are no asymptotes. Asymptotes parallel to either axis. This is parallel. If x raised power n and y raised power n are present, then there will be no asymptotes parallel to either axis. But if they are absent, then the next lower power of x and y, x raised power n minus 1, y raised power n minus 1, will provide you the asymptotes parallel to x as well as y axis. Next higher power means x raised power n minus 1 when equated to 0 gives asymptote parallel to x axis, and coefficient of y raised power n, coefficient x raised power n and coefficient of y raised power n when equated to 0 gives asymptote parallel to y axis, provided these are not constants. If they are constant, then there will be no asymptotes. You cannot put 5 equal to 0, 6 equal to 0. If x raised power n minus 1 is not present, then you have to go to x raised power n minus 2. If y raised power n minus 1 is not present, then you have to go to y raised power n minus 2. For example, say you have x square y, xy square equal x square plus y square. See, this is a cubic in x and y. This can be written as x cube x square y plus xy square minus x square minus y square equals 0. This is a cubic, you can write down. See, this is a cubic in x and y, wherein x cube and y cube are absent. So there may be asymptotes parallel to either axis. There may be, because if the branches are infinite, then and only then you will have an asymptote. Otherwise, if it's a finite branch, then you cannot have asymptotes at all. So, which are obtained? See again, this is x cube is absent, y cube is absent. So this is a cubic in x and y, where x cube and y cube are absent. So there may be asymptotes parallel to either axis, both x axis as well as y, which are obtained by equating coefficients of x square next higher power and y square to 0. Now, coefficient of x square equals 0 means See, x square, y and x square. What is the coefficient? It is y minus 1. See here, this is x square y minus x square. So x square times y minus 1. So this is the coefficient. This is the coefficient y minus 1. So this means y equal to 1. Y equal to 1. See, y equal to 1. Draw a line. This is an asymptote parallel to x-axis. So which is an asymptote parallel to x-axis. Similarly, coefficient of y square equal to 0 implies, now coefficient of y square, you have xy square minus y square equal to 0. This is x minus 1 y square equal to 0, means x square minus 1 equal to 0. Sorry, x minus 1 equal to 0 means x equal to 1. X equal to 1. This is x equal to 1. See, this is an asymptote. This line is an asymptote parallel to y-axis, which is an asymptote parallel to y-axis. Fine. So if you have an algebraic equation wherein x and yn are present and there is no asymptote parallel to either axis, then you have to go for the oblique asymptotes, which will be discussed today itself, how to find the oblique asymptotes. But if you don't have x raised power n and y raised power n, then you have to go for the next higher coefficients of x raised power n and y raised power n, which when equated to 0 gives us the asymptotes parallel to either axis, x-axis as well as y-axis, provided those are not merely a constant, those coefficients are not constants. Let me take one more example. Let us have, this is page number 17, this was 18 and this is 19. Let me have this question. X square y square equal to a square x square plus y square. This is, see, x square y square minus a square x square minus a square y square equals 0. See, this is x square y square means 4th degree. This is a 4th degree equation in x and y. This is a 4th degree equation in x and y, wherein x4 and y4 are absent. So I have to go to the coefficient of x cube and y cube. You can see x cube and y cube are also absent. Again, coefficient of x cube and y cube are also absent. So what I have to do? So the coefficients of x square and y square, which are both present there, coefficient of x square and y square, when equated to 0, gives us asymptotes parallel to either axis. Now, coefficient of x square equal to 0 means, we see you have x square y square and then a square x square. Now take x square outside. This means that y square minus a square equal to 0. See, x square y square minus a square x square. Coefficient of x square means y square minus a square equal to 0. So this is the coefficient. This gives us y equal to plus minus a. These are asymptotes parallel to x-axis. Similarly, coefficient of y square to 0, y square equals 0. Y square, you see, is x square y square, and this is a square y square. So it is x square minus a square equal to 0. So x equal plus minus a. So these are asymptotes parallel to y-axis. Let me draw a figure. X equal to plus a is this one, x equal to minus a is this one. So let me draw line. X equal to plus a minus a. These are asymptotes parallel to y-axis. Simple. Y equal to this one, y equal to plus a, and y equal to minus a. These are asymptotes parallel to x-axis. Simple. Let me take one more question. Y equal to x into x minus 1, x minus 2. So y is x into x square minus 3x plus 2, or y equal to x cube minus 3x square plus 2x, or x cube minus 3x square plus 2x minus y equal to 0. This is an algebraic equation. This is x cube minus 3x square plus 2x minus y equal to 0. See, this is a cubic in x and y, wherein x cube is present. So no asymptote parallel to x-axis. This is the rule. Now, y cube is absent. So I have to go to coefficient of y square. But y square is also absent. Y cube is absent. Y square is also absent. So what I have to do? I have to go to the coefficient of y. What is coefficient of y? It is minus 1. So y cube is absent. Y square is in, but the coefficient of y is minus 1, which is a constant and cannot be equated to 0. So there are no asymptotes parallel to either axis. This may contain asymptotes parallel to not parallel, oblique asymptotes. That will be told you how to find those oblique asymptotes. Let me take one more question. Say you have y cube xy square plus x square plus 1 equal to 0. This is y cube minus xy square minus, okay, let me, see, this is cubic in x and y, cubic, x and y cube present. So no asymptote parallel to y-axis. Now x cube is absent. So I have to go to the coefficient of x square, which is 1. Coefficient of x square is 1. So again, no asymptote parallel to x-axis. Now let me go to the oblique asymptotes. This is 20. Now for oblique asymptotes, we have a whole article that you need not remember that article, but the crux of the article is that algebraic equation can be written in this form: x raised power n phi n y by x. This I have just shown you. X raised power n minus n 1 phi n y by x plus so on x cube phi 3 y by x, x square phi 2 y by x, x phi y by x, phi 1 y by x, and phi 0. equals, this is an algebraic equation of an algebraic curve of degree n. And we say that let y equal mx plus c be the oblique asymptotes. M, you know, the slope, c is the y-intercept. We have to find m and c. You will get the asymptotes. That will be obviously oblique asymptotes. If you get a parallel asymptote from this also, that is already, we know that by the other method which we have already done. Now how to proceed for finding the oblique asymptotes? We have the method. See what is the method. We put x equal to 1 and y equal to m. It has a reason. You can go to the article. Then I will get phi n m equals 0. See, this is phi y by x. If I will put x equal to 1, y equal to m, I will get phi n m equal to 0. Similarly, phi n m. And then I can put x equal to 1, y equal to, we can get phi n m, comma, phi n minus 1 m, phi n minus 2 m, and so on. I can get all these, phi 3m, phi 2m, phi 1 and phi 0m. Okay. Now, equating, this is rule 1. This is this is step 1. Equating phi and m to 0, I will get m's, means the slope m. I will get m. For c, step 2, to find c, we use the formula c equal to minus phi n minus 1 m phi n dash m, or c square by factorial 2 phi n double dash m c phi n minus 1 dash m plus phi n minus 2m equal to 0. We use either this or this formula. This formula used only when c is 0 by 0 form, then we use this formula. Otherwise, we use this formula only. This is the method I will give you. I will send you the article. You don't need to know that article, but then you need to know the method. Now, let me take a question regarding this only. Let me take first one. Let me have, question is, find the asymptotes. Asymptotes, you don't have to, it is not given whether the asymptotes are oblique or parallel. Question is y cube x square y 2y square 4y plus x equals 0. Simple curve. Now let me write. This is a cubic in x and y, wherein y cube is present. So no asymptote parallel to y-axis. Simple. Since x cube is absent, there may be asymptotes parallel to y-axis, which are obtained by equating coefficient of x square to 0. Now what is coefficient of x square? It is minus y. So coefficient of x square equals 0 implies minus y equals 0 implies y equals 0. You see, y equal to 0. Where is y equals 0 is on x-axis. So this is an asymptote parallel to x-axis itself. So this is an asymptote parallel to x-axis, which is an asymptote parallel to x-axis. Now, this is one. This is a cubic, so other two may be oblique. For that, I have to, let me write it again. You have phi 3m. Phi 3m means these are the terms whose degree is 3. You have two terms only. M cube minus m equals 0. This is y cube, this is x square y, so degree is 3, so I have written phi 3m. X equal to 1, y equal to m. Phi 3m is m cube minus m equals 0. Actually, you can find first phi 3m, phi 2m, phi 1m. Let me find it here. Phi 3m, y cube minus m. Phi 2m, now those terms whose degree is 2. This is only one term, 2m square. Phi 1m, those terms whose degree is 1. This is 4m plus 1. X is 1, y is m. X is 1, y is m. X is 1, y is m. Now phi 3m equal to 0 means m cube minus this. This is m into m square minus 1 equal to 0. This is m equal to 0, m equal to plus minus 1. Okay, so you have 3 m's. Corresponding to 3 m's, you will get 3 straight lines, y equal mx plus c. Now phi 2m you already know. Now what is c? Minus phi 2m phi 3 dash m. Now minus phi 2m minus 2m square and derivative of phi 3m. This is phi 3m. Sorry, this is m cube. 3m square minus 1. Now when c equal to 0, when m is equal to 0, your c is minus 0 by 0 minus 1 0. So y equal to mx plus c means y equal to 0, which you have already found, y equal to 0. Because you cannot have more than 3 asymptotes. A cubic will have at most 3 asymptotes. 4th degree, 4 asymptotes. 5th degree, 5. At most. It may or may not have. Now when m is equal to 1, your c is minus 2, 3 minus 1. It is 2 minus 2 by 2. It is minus 1. So asymptote is y equal to mx plus c means y equal to m is 1, x minus 1. This is an asymptote parallel to, this is an oblique asymptote. When m is equal to minus 1, your c is minus 2 again. Minus 1 whole square is plus 1. 3 minus 1. So minus 2 by 2, it is minus 1. So the asymptote is y equal to mx plus c, y equal to minus x minus 1. This is an asymptote. So you have 3 asymptotes. 1, 2 and y equals 0. Y equals 0 was always there. So you have only 3 asymptotes. 2 are oblique, 1 is parallel. Page 20. Let me take page 21. Now the question is x square y plus xy square plus xy plus y square plus 3x equals 0. Okay. See, this is x square y, xy square. Both are of degree 3. Let me explain you so that you will not find any difficulty in future. Now 2 of degree 2. There is nothing of degree 3. So xy plus y square. These are of degree 2. Then you have only one term of degree 1. Now, let me write. This is a 4th degree equation. I will not write in detail. 4th degree equation in x and y. x4 and y4 are absent. So, there may be asymptotes parallel to either axis, which are obtained by equating coefficient of x cube and y cube to 0. But x cube and y cube are also absent. So we have to equate coefficient of x square and y square to 0. Now, coefficient of x square, see here, this is the question. X square, here it is x square and no, nothing else. There is no x square here. So, what is the coefficient of x square y? It is y. Coefficient of x square equal to 0 means y equal to 0. So, y equal to 0. You know why is y equal to 0? It is x-axis. So, this is uh, asymptote parallel to x-axis. Simple. Coefficient of y square equal to 0. Now y square. Here it is y square and here it is y square. Y square and y square. The coefficient is x plus 1. So x equal to minus 1. This is an asymptote parallel to y-axis. Y equal to minus 1 means this one. So is this an asymptote parallel to? Sorry, this is x equal to minus 1. X equal to minus 1 means this one. Parallel to y-axis. Okay, so you have two asymptotes. This is a 4-degree equation. Now let me reiterate again. This is a 4-degree equation. It may have 4 asymptotes. Two are parallel. One is parallel to x-axis, another is parallel to y-axis. So you have to find two oblique asymptotes. Now first highest order is phi 4. Now phi 4m. These are the terms having 4 degree. Sorry, this was cubic. Oh, yaar. Sorry, this was not a 4-degree equation. This was a cubic. Okay. This was cubic in x and y. X cube, y cube are absent. So coefficient of x square and y square when equated to 0 gives us two equations. Now, phi 3m. Phi 3m. The term was having the degree. Sorry. This was not a 4-degree equation. This is a cubic. X square y is cube, xy square is cube, then x square, xy and y square and 3x. This was not a 4-degree equation, sorry. Okay, now phi 3m. This is m plus m square equal to 0. Means m into m plus 1 equal to 0. So m equal to 0 and m equal to minus 1. So you have two values of m. Corresponding to two values of m, you will get two values of c. Therefore, two oblique asymptotes. Now c is equal to minus phi 2m, phi 3 dash m. Now minus phi 2m. You have, this is phi 2. And you have to replace x by 1, y by m. So this is m square plus m. Phi 3 dash, derivative of this one. This is phi 3. 2m plus 1. Now when m equal to 0, your c is minus 0 upon 1. So this is 0. So asymptote is oblique 1. Y equal to mx plus c. So y equal to 0 plus 0, which is y equal to 0. This is already known to us. Y equal to 0. Now when m equal to minus 1, c is equal to minus phi 2m, phi 3 dash m equal to minus 1 whole square is 1, minus 1, minus 2 plus 1. So it is 0. So c is 0. So asymptote is oblique asymptote. Y equal to minus x plus c. C is 0. So y equal to minus x. So this is an asymptote parallel to, sorry, this is an oblique asymptote. Oblique asymptote. Fine. Sorry. I had taken it at 4 degrees. This was a cubic x square y. This is cube. Xy square is cube. Xy square. So this is cubic. So I have to begin from this. This is a cubic in x and y, wherein x cube and y cube are absent. So the coefficients of x square and y square when equated to 0 gives us asymptotes parallel to either axis. Then for oblique asymptotes we have this formula. Fine. Page 22. Let me take one more example. Say you have y cube minus 2y square x minus yx square plus y cube. Oh, sorry. This is y cube minus 2y square x minus yx square plus 2x cube plus y square minus 6xy plus 5x square minus 2y plus 2x plus 1 equal to 0. Let me read it out again. Y cube minus 2y square x minus yx square plus 2x cube plus y square minus 6xy plus 5x square minus 2y plus 2x plus 1. See, this is y cube 2y square x minus yx square plus 2x cube. These are the terms having the degree 3. Okay. Now, these are the terms having degree 2. Y square 6xy plus 5x square. Now, there are the terms having degree 1 minus 2y plus 2x plus 1 equal to 0. Fine. This is it. 3, 2, 1 and go. Now, this is a cubic in x and y. Okay. Wherein x cube and y cube are present. So, there are no asymptotes parallel to either axis. So all the asymptotes may be oblique because x cube and y cube are present, no asymptotes parallel to